Okay, so this is our last major unit, Unit K. Unit L will be kind of a wrap-up unit, and then the final exam review. So if I'm doing my math right, there's this week, and then next week would be going into the Thanksgiving break, and then coming out of the Thanksgiving break, that's the final exam review lecture. So um, the unit during Thanksgiving break will not really introduce any new topics so much as review and synthesize. And then the week, the last week of class, then that lecture will be that final exam review, and then the other day of that will be the stage one of the final exam. And then stage two will be during finals week. But I'll give the kind of schedules for that as we look into next week. But to give sort of, I've already, I think I'm planning that stage one is going to be available starting on Wednesday of that week. So like Wednesday, Thursday, Friday. And, there's not, I could make it available Saturday and Sunday too. I'm sort of deciding on whether I want to do that, but at least Wednesday, Thursday, and Friday. And then stage two, I'm just going to make available all of finals week. And so if you would like to come here during the stage two final exam period during finals week, you are welcome to, but you don't have to. And you don't even have to take it on the day that period is scheduled for, because it will be available. Again, it's stage two, just like the midterm stage two. So it'll be open the whole time, open book, open notes, available for collaboration. And so, you could take it Monday and then be done with it, or you could leave it open the whole week and then submit your final one on Friday, and that's fine too. So that's the schedule kind of looking forward, a little more fine-grained. This is the last kind of real ICA. So this is the last one's kind of over new material before the ICA IMS, which are the final exam review ICAs. There is this homework J2 that's out, and this is the only homework that is not eligible to be dropped, and that there's no solution set. It is an arena-based homework. It gives you some exposure to this SS inventory management problem, which is actually it's a popular inventory management problem, and but solved using Arena. There are some output data tips that kind of remind you on how to get data out of Arena and work with it. It is an opportunity to use Process Analyzer or OptQuest, but certainly you don't have to. Otherwise, there's no more lab experiences. So basically, the lab times and the time savings you get from not having labs is meant to provide you extra time to work on that final project, so you have a nice solid final project, and should absolutely feel free to make use of the TA to get help with that final exam project for sure. But there's no formal lab schedule from this point on. Otherwise, final project, I talked about sufficiently complex before. Again, the main big deliverables will be that middle of the week during the last week of class. That's when the Wednesday night, the presentations and final report are due, and that will give time for everyone to do their peer reviews then, which will be due Saturday. Otherwise, then the only other ICAs that are on the books are the final exam review ICAs. This is similar to the midterm review ICA, where it samples from all of the post midterm ICAs, samples randomly from them. It's a little bit longer. You can take it as many times as you want. You get your highest score. So it's meant to help be a review exercise. And then, as I was just mentioning, the final exam is this two-stage exam. They're both going to be, designed for 75 minutes, even though the final exam period, is technically longer, but because we do it as a two-stage and it overlaps with the normal class period, then it's going to be the same length as the midterm, basically. So the content will be cumulative, but we'll have emphasis on the material since the midterm. So, we've talked about chi-squared before and after the midterm. So, I'll just talk about it in the after midterm state. We've talked about KS test before and after the midterm. So we'll talk about it in the after state. We've been talking about simulation before and after the midterm. So, a lot of the topics that were before the midterm, we've just kind of extended and added to them. So it is technically cumulative. I do want you to remember how to do a hand simulation, for example. So do expect to have another hand simulation problem, probably just one on the final exam. But most of the material will bias towards the more advanced kind of topics that we've had since after the midterm. So, questions about any of that? Okay, I want to make sure something over here. Okay, and then one more thing. I want to double check what I've done over here. Good. Okay, so um, what I've been trying to, speaking about the final project, I want to make sure that in all of your final project reports, you're using interval estimates. So I don't want you to say that we ran system A, we ran system B, and system A had a mean waiting time of 6 minutes, and system B had a mean waiting time of 5.5 minutes. So obviously, system B is better than system A because those point estimates, so an estimate without an interval, just a single point, if you were to rerun that simulation with a different random number seed, you might get a different ordering. So you can't infer anything about point estimates. So whenever you get data, as long as they're generated from independent replications, you can always add a standard error of the mean. And if those data are also normally distributed, as most of the data will be that come out of your simulations, then you can also add a confidence interval. So that's what we're trying to sort of get in the habit of using these confidence intervals, because when you're talking about empirical methods, if you run that experiment, whether it be a simulation experiment or an experiment in the real world, a single sample average from that experiment doesn't tell you anything because you don't know about how variable that sample average would be if you were to rerun that experiment. So you definitely can't order things just by those points. That's why in your final exams, I'm going to expect, or sorry, your final projects, I'm going to expect to see you report intervals, at least intervals, not points. And so we talked about that confidence intervals capture uncertainty. It even applies to linear regression. So, we fit a line to a bunch of points and we think that that's an approximation of those points. But even, if we took more data, then it's possible that that line might have a slightly different tilt to it. Might tilt slightly more steeply or more shallow. And so even this estimate of the slope of that line, which is the relationship between these two variables, itself should always be bundled with a confidence interval. So confidence intervals, they capture sort of a t-test. They, all in one, nice entity. So you know that anything inside the confidence interval would fail to be rejected by a t-test. Anything outside the confidence interval would be rejected by a t-test. So we, talked about if you have to an absolute performance estimate. So I've got one system here, and maybe I've got caller wait time and sample variance. Then I form a one sample confidence interval, which I can then compare to hypothetical performances. And so if I say I've simulated your call center and these callers have an average wait time of 5.5 minutes plus or minus a half a minute, what you're saying there is in my little simulation, the average wait time was 5.5 minutes, but I could run my simulation multiple times and it would give me different average wait times because I'd have different callers every time I ran it. But I'm pretty confident that the real wait time, the real mean of the wait time is falls within this interval of 5.5 plus or minus half a minute. So, and I'm pretty confident that so that means that if you were to ask, is there a possibility that the wait time is 4 minutes? And I'd say, well, sorry, 5.5 minutes, minus a half is still well above 4. So I don't think there's any chance that the real wait time is 4 minutes. So that's what our confidence interval tells us for absolute performance. Anything outside the confidence interval, we're pretty sure is not it. Anything inside the confidence interval could be it. But we're never estimating a point. We're estimating where the real performance measure likely is. We don't ever know exactly where it is, but we know that it's probably in that interval. So in order to generate this confidence interval, we have to know the degrees of freedom from so in this case, for a one sample absolute performance measure here, it's always going to be just R minus 1 degrees of freedom, the number of replications minus 1. We have to then calculate the standard error of the mean. which for independent replications, we can always calculate. So an estimate of the standard deviation divided by the square root of the number of replications. And then once we have those, then we can look up the critical t statistic value in a table that corresponds to this many degrees of freedom. And we basically can then scale the standard error of the mean by that critical t value. And that's how we get the half width, which is, half of this confidence interval up here, this half here and this half down here. So those are the critical things to calculate confidence intervals, is to figure out for the particular experiment you ran, what is the degrees of freedom in your estimate of the mean, and what is the standard error of that estimate of the mean. So useful tools is, once you have a confidence interval, you can convert from one confidence level to another just by scaling the confidence interval by those critical t levels. So if I have a half width for 95% confidence interval, I can effectively divide off the critical t value I used to get that half width and then multiply it by a new critical t value. So this is how I go from a 95% confidence interval to a 90% confidence interval, as an example. And then other useful tools is, if your stakeholder tells you that I want you to run, give me enough certainty so that I understand you can't tell me what the actual performance measure is. I get that. But I would like you to give me confidence that the actual performance measure is within 1 minute of your estimate, something along those lines. They're effectively giving you a bound on the half width of your confidence interval. So you can kind of back out to say, well, I know the confidence interval formula. I'm going to approximate the t distribution with a normal. And I've got a little formula here where I run a few replications to get an estimate of the standard deviation of the real data. And then I run it through this little formula here. And then that will give me a lower bound on the number of replications to get their desired half width. And I might need to run a few more, but this will at least get me in the ballpark. And I can subtract off the number of replications I ran in order to generate that standard deviation. So that's for our absolute performance measures, how we generate those confidence intervals. So is that all clear for absolute estimates and how confidence intervals fit in and all different ways you can use them? So if you're doing absolute performance estimation on your final project, again, I don't want to see a table. It's the worst thing when you see a table and they're like model A, and then it just says like performance measure, and then it just says 5 minutes or something like that. Model B, 6 minutes. Like, don't do point estimates per model, because you can't actually compare point estimates, because point estimates, they don't give you any idea of how much spread there is in your data. Always do at least confidence intervals, if not a more sophisticated test. Okay, so then the relative performance, which a lot of times for your final projects will actually be easier to make a compelling case for. Because when you do absolute performance measures, you are really making an inference on the actual performance in the real world, which means you have to have a really accurate simulation model, a model that you're pretty confident is calibrated well to the real world. And sometimes if you're working on this for just a couple of weeks, it's really hard to get a well verified and validated model. So instead, you could say, well, I don't actually know if model A and model B, where model A is maybe the as-is system and model B is my new system, match the real world perfectly. But I do know that if model B is better than model A in simulation, model B is probably better than model A in the real world. So maybe just knowing the relative ranking of model A and model B in sim is enough. So then, relative performance measures can be easier or more, easier to justify. And so idea here, I've got a system 1 call center with these specialists, system 2 call center with cross training for the generalists. And I've got, a mean for specialists, a mean for generalists, a standard deviation or variance for the two groups as well. So then there's 3 different ways that I could calculate confidence intervals, depending on the 3 different experiments that I could run. So I could run an experiment where I run the same colors through both systems. So that would mean that the performances of every system would be form blocks, where this group of colors generated a performance from 1 and a performance of 2. And then another group of colors generated another performance from one, another performance from two, and so on, where every block of colors generated one performance measure from each. And that would then have me do an inference on the difference between those. So for each block, I would subtract the two performance measures and generate a single difference. And my confidence interval would be on those differences. And I would use then a paired difference confidence interval, which is derived from a paired difference t-test. And the idea there is that I still calculate the confidence interval with this same formula that I just did with effectively the one sample, but my degrees of freedom is R minus one, just like with the one sample. My standard error of the mean now is the standard deviation of the differences divided by the square root of R. So this is basically exactly the same as the one sample confidence interval, but I'm doing it on the differences and not the individual data. Now, alternatively, I say that's not how I ran my experiment. I ran a separate set of customers through system one and a separate set of customers through system two. And I'm comparing these two with these separate set of customers. In this case, the performance measures from system one are unrelated to system two. There's no obvious pairing. And they're just sort of, these are just random. This is like, I might have 20, or I might even have a different number. I might have 25 performance measures here and 20 performance measures here. So there's no way to pair them up to calculate differences. So in this case, I really need to say, does the mean from this distribution, is it likely to be matching or different than the mean from this distribution? So my question before I can go forward is to ask, do these two groups have the same variance? And there are tests for that, like the Levine's test is a test that sometimes is covered, I think, in 380 or 385. There's a bunch of others, or the F test is, I think, one that is probably covered in 380, 385. But there's a bunch of different tests that say, do these two groups have the same variance? If they do have the same variance, then you can pool all of those samples together for the purposes of getting a better estimate of the variance. The means are separate, but you gather all the data together in the variance formula, in which case the degree of freedom that you plug into this formula is the number of samples from experiment one plus the number of samples from experiment two minus two instead of minus one. And then the standard error of the mean is this beast here. So it's a little ugly, but you can work through why it makes sense. And then so you calculate that standard error of the mean, those degrees of freedom, and then you calculate the half width exactly as you always do, and you treat it the same. So because these are difference half widths, then really the big hypothesis you care about is whether zero is included in these confidence intervals. So if zero is not included, then there's a difference between the systems. If zero is included in the confidence interval, then the systems, you can't discriminate between them at this point. You can't say one is better than the other. It could just be random chance. But if zero is outside the confidence interval, it does also give you a little bit of an estimate of how different the systems are. They could be this close together or this far apart. All right, so that's the pooled variance. Now, you might run this test and find out that system one is far more consistent than system two for whatever reason, just how it's built. And so in that case, you can't use the pooled variance t-test, basically the pooled variance sample confidence interval. So instead, you have to go to these formulas down here, which is what you do for the unequal variance confidence intervals or the Welch's two-sample t-test. So these are just equivalent here. And so this is an ugly formula for degree of freedom. I actually think I meant to put a floor around that. I think that's necessary. I might go in and fix that. I'm not expecting you, by the way, to memorize these formulas. I do want you to know when you're supposed to use these difference, because I have confidence that if you needed these, you could look it up. Like, what are the degrees of freedom for a Welch's t-test? There it is. But, or more likely, you're going to load into a statistical tool like Output Analyzer and say, I've got two data sets, compare them. And it'll say, how do you want me to compare them? As paired differences, as pooled variance, or as unequal variance? And then you'll know why it's asking you those questions. So not expecting you to memorize these formulas. But nevertheless, that's the formula for degree of freedom. That's the formula for standard error of the mean. You calculate those, you plop them into the half width, and you have your confidence interval. So that's how we do relative differences with confidence intervals. So questions about that? So review of last time. Okay. So then I'm just bringing this up here because like showing this idea that I'm comparing this confidence interval to zero. So, and a lot of times I pull up these academic articles because it's an easy way for me to show how these are used, because it's not like I have a lot of industry case studies where I can say, here's a report, an internal report from this company to show how they manage this data. So instead, it's just easier for me to go to scientific literature because they're doing the same sort of things. And so if you were to sort of zoom in on this particular paragraph of this empirical paper here, then we see that they report in text that they have these, yeah, that two of the three data sets, Lilith, two, doesn't matter what these are, and Hermione, it says, Lilith 2, it talks about they did a paired t-test, and they report the mean difference right there, paired t-test, and they report mean difference. So it's just showing you that they're reporting differences. And this mean difference happens to be negative, but then they give 95% confidence intervals, negative 0.2 to positive 0.061. And so the fact that zero is included in there tells you that you can't conclude that there's any difference between that group. And they didn't even report a p-value. They just said the confidence interval includes zero. You're supposed to know that as a data scientist, you're just supposed to know that if someone shows you a confidence interval that's for mean differences and it includes zero, that the p-value is effectively greater than 0.05. That's just supposed to naturally be there. It's our language. So then, likewise down here, they did the same thing. So these are not significant. So notice it says NS, not significant, NS, not significant. And that's because the confidence intervals include zero. Whereas down here, they say, but in this group, we have a one-tailed, whatever, 13 paired t-test, mean difference. This is a negative mean difference, just like this negative mean difference. But then they say 95% confidence intervals. This confidence interval does not include zero. So that is why it has a p-value less than 0.05. So it has a significant difference. So, you report, I have my mean difference, and sometimes for convenience, you'll report the average mean difference. But the important thing is the confidence interval and whether it includes zero. So that's what you report. That's what you should report on your final reports as well for your final projects. Now, if you're doing paired t-test, or sorry, a paired design, then it's very common to actually plot, if you have a small number in particular of groups, to just plot all the groups paired together. So like in this particular case, this is something where this is system A, this is system B, this is the common input to both. And so they plotted all of the inputs down here, and here we see that, let's call the X's system A and the circle system B. Pretty much all of the X's are on top. So except for this one case, which they used a dashed line to highlight, all of the X's are on top, kind of giving you the idea that although for each individual input, there is some variability in how different things are. It looks pretty consistent, though, that the ones that's marked with the X's always are larger in this performance variable. So that is a nice way to sort of summarize that. It's showing you these differences and that these differences are generally always positive. So that is a nice way to plot paired data. If they're not paired, then it wouldn't make sense to plot them that way because you'd be picking arbitrary pairs that aren't actually related to each other. So if they're not paired, this is the way you typically would summarize that. You'd say, I've got my group over here, I've got my group over here. You could use a box and whiskers plot like this, that's fine. You could use a plot the mean plus or minus the confidence interval, the half width. That would be totally fine too. But you summarize the spread of the data. And then if is a significant difference between them, you often indicate that either by like drawing a line over top and saying P is less than 0.05, or you might draw a line over top and just simply put a single asterisk. And that's kind of the symbol, is that an asterisk typically means that these two groups are statistically different from each other. If there's no asterisk, then that means it might look like they're different, but the test says that we can't conclude that they're different. But in this case, there are different. The P is less than 0.05. So if you were to apply confidence intervals here, these confidence intervals would probably not overlap, because if they don't overlap, we can infer that P is less than 0.05. So that's how we would do it with two sample unpaired tests. So that's the paired case. That's the unpaired case. So questions about these visualizations? We've actually seen these visualizations. I've actually plotted this for the muffin baking simulation in a very similar way, where we had the different random number streams that corresponded to the last digit of your ASU ID. So each one got a different number stream, which effectively gave you different muffin schedules. And then so we had schedule 0 through schedule 9. And for each schedule, you ran them through both muffin batches. So you had like, this is the kind of greedy strategy, and this is the one where it waits until it's almost full. And then we plotted one performance measure out. And so for each batch, we could calculate a difference. And then we had 10 differences, one difference per schedule. And then we made inferences about the differences. So that's exactly what's going on here. Okay. Then, we talked about, two or more, comparing them in a relative way. Things get a little hairier. And if you want to do it in a rigorous way, fortunately in engineering, because we're okay with inflating our alpha, inflating our type 1 error, because most of the time when we're doing engineering R&D, we're going to follow up with more money to do further investigations, then we're okay with getting false positives, because false positives, we would rather not miss an opportunity that we can exploit and tune and grow into an advantage, a competitive advantage. But so because of that, some like treating three or more groups as if they're two groups will inflate that type 1 error, but in some cases it's not going to hurt us, because again, we're screening anyway. But this is going over the most kind of rigorous way to do this. If really we're at the end of it and our boss says, this is the only money that I'm going to put into operations research here is your study right there. You need to tell me the be all and end all of which one of these is best. And then we're done. In that case, I better get it right. And so that's why we care about these next couple of methods. So I got 3 systems, so 3 sample means and 3 sample variances. So one of the things that this generally fits into the category of ranking and selection. So I want to, if I could, one of the things I can do is compare all of the models to each other. So every single pair I can compare to each other, and then use a 2 sample t-test basically to do that. So in that case, I'll have this many comparisons, which grows very fast as the number of systems grows. And then, but in order for me to make it so that I don't accidentally choose an ordering and say this ordering is like, I can accidentally order them in ways in which that I thought based on the data that one system is better than the other, but it just happened to turn out that way by random chance. And so that's a false positive there. In order for me to guarantee that my detecting of an ordering has a false positive rate of only 5%, I need to decrease my false positive rates of my individual tests by a very large amount. So basically, I use this Bonferroni correction. And so each individual pairwise test comparing, so when I compare 1 to 2 and 2 to 3, and then 1 to 3, for each one of those individual tests, because I do 3 total tests, I need to use an alpha of 0.05 divided by 3. And by doing that, then when I end up finding out that 1 looks better than 2 from that comparison, 2 and 3 aren't that different, 1 and 3 is better than 3, and so I decide to rank them so that 1 is best and 2 and 3 are I can't tell the difference. And then so then I come back to the boss and I say one is best, then I can be confident that there's only a 5% chance that I put one in the best spot when actually that was just random chance for the data that I had. And in order for me to really be that confident, I need to expand my confidence intervals. I need to make it harder to see a difference between one and two, because I'm going to be fishing for all of these differences. Because I'm going to look for, because I'm doing all of these comparisons, in order for you to get the final ranking right with 95% chance, I need to then be much more conservative about the individual pairwise rankings. That's what Bonferroni correction is. So if you have a bunch of comparisons, it's just dividing down that individual false positive rate by your number of comparisons to be safe. So questions about that? Does that make sense why we have Bonferroni correction there? It's to prevent phishing, accidentally finding a difference in a large group because you've used multiple comparisons to look for that difference. Okay. So the alternative, the more sophisticated alternative to Bonferroni, which a lot of times you can't do this if your data have particular features. Fortunately, with a lot of sim data, it's fine. Real world data, sometimes these more sophisticated methods are not available. So you end up always having to, not always, but you have to default to Bonferroni. It's like that's your backstop. Like if worst comes to worst, I'll do Bonferroni correction. I'm going to lose a lot of statistical power, so it might wash all my signal out, but at least I've got that I can try. But the alternative here is to use an ANOVA. So this is an analysis of variance. The idea here is it's sort of like a generalization of a t-test. So rather than having two groups, you have multiple groups. And so I've got my system A, my system B, my system C, system D, and system E. And I'd like to know how do these five systems rank? Or I've got system A with one cashier, two cashiers, three cashiers, four cashiers, five cashiers, something like that. Either way, I've got five groups that I'd like to see how they rank. And so you run the ANOVA, and the first thing the ANOVA will tell you is if there's a difference at all among any of your groups. It doesn't tell you which one's better. And it's not telling you can trust the way things are ranked by their means. It's just saying, is there a difference or not? If it comes back and P is greater than 0.05 out of the ANOVA, you can't, there's no difference between these groups. You have to stop there. Even if it looks like there's a difference, these type of data could still come back and it say, based on the variance, there's although you might see a pattern if you squint, there's actually no difference between here. This is that it's all just due to random chance. But if it comes back and says there is a difference, then you can run what's called a post hoc test. And there are a couple of different post hoc tests that are commonly used. There's the Tukey significant differences test here. There's also Fisher's LSD or HSD, and so there's a bunch of different Tukey or a bunch of different post hoc tests, and they run. There's different reasons to use them, but they all basically do the same thing. Just some are sort of more type 1 error than others. But the idea here is that the post hoc test will then do the sorting for you. So after you run the Tukey test on this ANOVA result, then it puts these letters up here. And the way you interpret these letters is if two groups share a letter, then the pairwise comparison between those groups is insignificant. There's no difference. If they don't share a letter, then the pairwise comparison between those two groups says that there is a difference. So when I look at this, I see that system A and system B, I can't tell the difference between them. System A and system C, I can't tell the difference between them. But system A and system D, there is a difference. Interestingly, system C and system D, I can't tell a difference between them. And system D and system E, I can't tell a difference between them. So if they share a letter, there's a B there, there's a B there. So if you can't read those A, B, B, and B. So whenever you share a letter, there's no difference. Whenever you don't share a letter, there is a difference. And that allows you to then do a little bit of ranking here. All right, so that's what we mean by a post hoc test, and that's what those little letters mean if you see those in this sort of output. Yep. Right. Well, so and that's the reason why we have the test is that so when we look at this, it's tempting to say this looks like it's far enough below this one over here. But when this Tukey test was actually run, then when you look at all five of these groups together, that apparently this variance, that based on the pivotal distribution that is sitting behind this, which this is ANOVA is built on top of an F test. And so there's some T type distribution, then it's saying that that it can't differentiate between this group and this group. It seems like, well, there's enough of space, or I guess what I'm saying is like there is enough space between A and B for these to clearly be different. But even though there's a little bit of daylight here, it's not enough daylight to differentiate this group from either of those two groups. That's exactly why we have to result to these tests, because if we just plot these, it's really tempting to say this, but if we want to make sure our false positive rate is 5% or less, then we have to run these tests. Because it might be that your inference that it really looks like AB should be different than these. You might be right. If I were to crank my alpha up to 10%, this might be A, B, C, D, E. But at 5%, with that, if I want 95% confidence, then the best it can do is to say, I'm not really sure about splitting up these three. Great question. Any other questions about that? Okay. Now, for sim, this is not ideal because with an ANOVA, you need to run all of your replications, then run your ANOVA. What we would like to do for sim, because our sims might take a while, is we'd like to run like 10 replications, see if we can sort out our models. And if we can't sort them out, run another 10, run another 10, run another 10, and keep doing this until finally we've got enough data to say, okay, we have a sorting that we can be confident in. That's referred to as sequential sampling. And so we often also need to just find the best model, not the full ranking. So both of these reasons are why ANOVA, it's great for if you have a bunch of data and then you are interested in the sort of how much of an effect these different groups do. But if we're engineering, we often just want the best model, and we're willing to sort of trickle in more experimentation as needed, especially with simulation. So that's why there are these select the best procedures, for example, which will automatically be able to do this, to sort of just select one best, and potentially be able to do it by just trickling in replications and only running as many replications as you need in order to select the best. So there are these other methods that are built into these tools. There are algorithms. I don't know if I've got one summarized here, but in the previous lecture, I didn't go through it because I don't need you to memorize it. But in the book, in the Banks book, they go through a select the best procedure that does like have you run a pilot number of replications, analyze those, and then as needed, run another set of replications in order for, it basically estimates variance with the pilot and then says with the pilot, if you want to know the best, and that's all you care about, then all we need is 15 more replications. And then it will then you run the 15 replications and it can select the best with 5% error. So that's very different than ranking the whole thing, than ranking and sorting the whole thing. And then likewise, Arena's got this in the process analyzer. You can put in 3 models or 3 different configurations of the same model. That's what's happening here. Have it, you can tell it how many reps that you would ideally want it to run. Tell it to run. It will then automatically run all of those for you, so you don't have to do it. And if you tell it you want it to plot a box and whiskers, then a bonus of the box and whiskers output in the process analyzer is it will ask, do you want me to select the best? And if you say yes, then you say, well, it'll say, is best high or low? And you say, well, in this case, it's high. And then it will give you this thing, which looks a little bit like an ANOVA with a post hoc test, where it will highlight groups that it can't differentiate from the best, and it will highlight in another color groups that it can differentiate from the best. So in this case, you've got the best here has been configured as lowest. So it's actually saying that this blue thing, don't do it. But this red thing, do either one of these, and that's the best. I can't tell the difference between these red, but both of these red are way better than the blue. And that's what this select the best procedure does for you. It doesn't rank the whole thing, but it does separate things out so that we know that I shouldn't regret choosing either of these scenarios based on the data I have. All right, questions about select the best, the difference there? And then the last thing about automation is OptQuest and Arena. This is a really cool tool in that you can go into OptQuest and you can say, here is my model. Here are constraints that I just want, here's my model and here are all the decision variables that I'm allowing you to change on your own. I'm not telling you what values, like I'm not telling you how many cashiers I want you to sweep through, but I do want you to try the number of cashiers. So try any number of cashiers from 2 to 20. I don't want you to go higher than 20, I want you to go lower than 2, but do whatever you need to do. Number of lanes, any number of lanes from 1 to 10. You could come up with these decision variables and you give it bounds, and then you just say go. And then what it does is, and then you give it constraints as well. And you can say that I only want to consider solutions whose wait time is less than 10 minutes. So there might be another way that you can optimize my profit, but if you optimize my profit, but my customer wait time is greater than 10 minutes, I can't have that. So you can also put these constraints in there. And then you just tell it to go, and it will just start at a random point in your decision space. It will run as many replications as it needs using that kind of select the best to make a conclusion about that set of parameters. And then it will change the parameters in a way that probes the system. And then it will learn whether it made an improvement or not. And then it will change the parameters again. And it will keep doing that over and over again. And if I'm minimizing this performance measure here, then I can see it goes, this red, this is infeasible, gets back into the feasible region, and then it manages to find a way to minimize it. So this is a way to do automated experimentation where you say, I have no idea what set of parameters is going to be best for this. I want you to explore the space rather than me doing a Latin hypercube sampling or something where I have to do a huge number of replications. This greatly reduces your simulation time because it doesn't force you to do every possible thing. It tries to intelligently choose things based on how well things have done on past trials. So that's what OptQuest does. It's a pretty cool tool. If you can get it to work, sometimes it's a little finicky trying to get it to open in later versions of Arena. Okay, and this is a licensed tool. This is not made by, most of this has been then imported or licensed by Rockwell Automation. There's another company that makes OptQuest. So you'll find OptQuest in other simulation tools as well, like AnyLogic, which is the tool they use in 477. All right, so any questions about all that? That's the kind of review. Okay, all right, so our last unit here, split up into two lectures here, VRT, variance reduction techniques. So these are ways in which we try to make our simulations take less computational time by adjusting the experimental setup in some particular way or processing the data in some particular way. So where does this come from? So, going back to what we were just talking about, if we have this performance measure that we're estimating with a mean, we have, that estimator of the mean has a certain standard error. So every time I recalculate this mean, it has a variability in it, and this captures the standard deviation of that variable estimator. So if I look at this as a fraction, and so far I've been talking about, reducing the size of the confidence interval by increasing the number of replications. Well, that's one way to do it. But alternatively, it would be great if I could just reduce the standard deviation, reduce the intrinsic variability in my system, or at least in my experiment. And that's what VRT is about, is to use experimental design to control for other sources of variance that we don't actually care about, so that we can focus on the sources of variance, i.e., the difference between our two systems that we do care about. That's what VRT is all about. So we're going to talk about 4 different ones that common random numbers, control variates, antithetic variates, and importance sampling that all allow us to do this. Today, we're focusing on these 2. So we've already kind of talked about common random numbers. This is just our paired difference t-test across two simulation replications with effectively the same inputs. So the idea here is we create a blocked experiment. So this is all review. So I run this two models with the same number of replications. I put the same input to both models. For example, I use the same random number seed. I'll show you how to do that here in about a slide or two in Arena. And then this allows you then to control for differences in the output that are only due to differences in the input. In other words, if I see a performance difference between system one and system two, I want to know that's because system one is better. It's not that system one got a luckier set of customer inputs. So that's why running the same customers into it to control for the variance due to the inputs. And so this only works if my two systems respond the same way to the same inputs. That will, in other words, it only works if I can induce a correlation between my two systems. So if I happen to have two systems that both take longer for the same input, if there is a generally hard input that makes both systems take longer, this is perfect for that. Because then I can account for the variance due to the changes in input. But if it happens to be that system one is tuned for one type of input, system two is tuned for another type of input, so there is no common way to get them to both, behave poorly on certain inputs and behave well on another set of inputs, then this is not a way that I can control the variance. Now, so this isn't always going to work, is what I'm trying to say here. And you will have to run pilot tests to make sure this is working before you count on it. So the math behind here is that the variance and the difference between two systems is the variance in one system plus the variance in another system minus effectively the correlation between the two systems. So if there's no correlation, then there's no reduction in variance. So that's, and if I can reduce the variance, then I am going to get a tighter confidence interval on the differences. I have to use a paired difference t-test, so paired difference confidence intervals to make this work. We saw this in the muffin baking simulation back in whatever that was, lab 2. And so, I had a greedy system and a nearly full system that I wanted to compare. We had different schedules, 10 different schedules. So each schedule was run into both of these systems. And so we can pair them together. So the lines connect the outputs that corresponded to the same input. So in reality here, it looks like I have 20 outputs. I have 10 outputs from greedy, 10 outputs from nearly full, but I don't. I really only have 10 outputs. I have a difference corresponding to this muffin schedule, and I have a difference corresponding to this muffin schedule, and so on and so forth. So there's really only 10 data points that I have to work with here. So I could, instead of plotting them in that fashion, I could plot them like I showed you before, where this is for schedule 0, this is the greedy performance, this is the nearly full performance. So you can see here nearly full is almost always, well, it is in this case always on top, greedy is always on bottom. So these differences all have the same sign. So I run a t-test on the differences to see if they contain 0. They're almost definitely not going to contain 0 because they're all they all have the same sign. So here are all of those differences. So in this case, when I do greedy minus nearly full, they're all negative. So if I calculate a confidence interval for these data, it will be a confidence interval that does not include 0. And so I can conclude that one system is better than the other. And so this is another example of exactly that from the book. Here is independent sampling. So imagine I ran a different muffin schedule I had 100 muffin schedules that I ran into the greedy, another 100 muffin schedules totally independent that I ran to the nearly full, and then I plotted those and I arbitrarily paired them up. And you see sometimes the circles are on top, sometimes the circles are on bottom. So there's no obvious pattern. And so there's no reason to pair them up this way. But once I use common random numbers, then suddenly these giant differences I see are not due to true differences in the system. So here you're like, wow, maybe this system is really much better than this system. But then you look over here and you see the opposite pattern. Well, I'd say, well, or that could be just due to being unlucky with the inputs. So if I then give them all the same inputs, then I see that actually when I give them all the same inputs, there's hardly any difference between these two systems. So that controls for the variance on the inputs so that I can extract the variance that's due to my different systems. And in that case, it's very small variance. So I can now detect a smaller effect size so that I can better estimate the true effect between these two systems. That's the power of common random numbers. So any questions about that? About why, this turns into that and what just happened there and why that's a good thing? Okay. Yep, I'm sorry. What do you mean if it's high or low values? There, well, we can't decide if there, so the idea here is if you have a high amount of variance in your two systems, the only way that you can detect, let's say that you know that system A is only a little better than system B, and you would like to estimate how much better system A is than B. If there's this much variance, in order for you to estimate how that little difference, you're going to need a lot of replications. You might need thousands and thousands of replications in order to average out all of this variance so that you can detect that small difference. But if you then make the hypothesis that, well, actually, most of this variance isn't due to variance in the systems, it's due to variance coming from outside the system through the inputs, then I can run the same inputs into the same systems. And then now I do see tiny variances that much tinier than they used to be. And all of the black dots pretty much are on top of the open dots. And so that tells me that if I were to do this t-test, I probably could tell that, well, this open circle system, system two, is significantly lower than the closed circle system, system one. So it's not so much that I'm not setting the variance, but I'm trying to understand, is the variance due to the systems or the inputs? And when I subtract out the variance of the inputs by pairing them together, then I can now detect the true size of the effect between the systems. Here, it really could have been that sometimes system one is much better than system two for reasons having to do with system one. But here I see that, well, actually, that system one is pretty much always a higher measure than system two, and there's just always a very low difference between them. So once I account for the input differences, then maybe each one of these sizes is not actually practically important, and I could just tell my stakeholder, if system one is your as is system and system two is your proposed system, then just stick with your as is because it's not going to be worth the cost of re-implementing your proposed. Does that answer your question? Or and in this particular booking case, the difference between these two systems is a one server queue versus a two server queue. And what this is telling me is that there's probably so low utilization in the system that adding another server doesn't actually help very much. And so the variances that I see here are just due to kind of customers that have, just bursty traffic. So in this system happened to have a burst of traffic, whereas this system didn't, and vice versa here. Okay, so how do we do that in Arena? So in Arena, you have to bring in this elements panel, which you don't get automatically, but you can right click on this, add panels, bring that elements panel. Then there's this old seeds panel that you bring in. It looks very different than all the other Arena panels, but because it's more fundamental, it's been there for a very long time, and it allows you to configure the random number seeds. We've talked about this a little bit before. The idea is you drill into the seeds panel, you can add a seed, and you can then either add your own named stream, or you can use 10, which is the default number stream. You can put a seed value in, but it doesn't matter if you, I mean, if you prefer, but you don't need to. And then under initialize option, this is the new thing. you can then say, you click on this box here and you say common. And what that's going to do is every replication, it's going to choose a seed that is, I think it'll say in the next slide, 100,000 more than the seed it used for the previous replication. So without common, then basically it runs through the first replication, and then the seed for the next replication is a function of where it left off in the previous replication. So there's if one model's replication runs for a different length or draws a different number of random variables than another model's replication, that replication number, then you can't guarantee that they both start with the same seed. This guarantees that regardless of how many random numbers were drawn in your model, every replication's initial seed will be the exact same difference from the previous seed in the previous replication. And that helps synchronize these random number seeds. And so that's what I'm saying here, is that if you do common, then that ensures that the seed for the next replication is exactly 100,000 apart from the seed from the previous replication. And that allows you that even if you're running one model and you close it and open up a new model, if they're both initialized the same way and they both have the same starting seed and then have this same common, then if you run 10 replications of one and 10 replications of the other, then they'll all have the same random number seed into every replication because this is forced. Questions about that? Does that make sense? That's how you implement common random numbers in Arena. There are similar features in other simulation tools. Of course, you can manually do this if you have access to if you're doing a sim in Python or whatever, then you can, of course, grab that random number seed and then change it yourself in a similar way. Okay, so then how do you use that? If you use 10 as your seed name, it's automatically baked into every single random number, but very often you just want to affect the random numbers picked in your create blocks. So that's why you might want to create a named stream or called like interarrival distribution or something. And then that's the one that has the common random numbers. That allows you to draw, like, let's say you've got decide blocks and stuff that draw their own random numbers. Well, they can then use another stream that doesn't corrupt this one. And that helps ensure that the create block across all of your models generates the same number of customers, and it allows you to still use random numbers from other seeds or from the default stream in the rest of your model. Questions about that? Okay. So that's all I'm summarizing here, is that every one of these random number distributions takes an optional argument, which is the stream that's identified in the seeds module. So you can name one and put it in there, and then that will give you exponential interarrivals for the create block. But if you draw other random numbers in the rest of your model, as long as it's not using this stream, then it's not going to corrupt this draw. So that helps ensure that if you draw 100 customers, they'll always be the same 100 interarrival times. Downsides of CRN, I've already kind of mentioned this, it doesn't always work. So there's no general proof that it'll reduce variance. So you generally want to run pilot runs. So you run a small number of paired replications, estimate the variance of a single replication, one, model two, and the difference between the models. And then just see, is the variance of the difference less than the sum of the two variances? If it is, then that's a good indication that CRNs will work for a larger experiment, and you can maybe crank the replications up. But if it isn't, then maybe this CRN stuff isn't actually beneficial to you, and you may as well run them independently if that's easier, or there's other reasons for you to prefer that. Okay. So questions about CRNs? Okay. So let's then, the last one that I want to talk about today are control variates. This won't take very long, but, and so control variates, you can also apply this. It doesn't just apply to simulation. It could apply to other sorts of data. It can be applied after the fact. You don't have to necessarily redesign your simulation experiment to make them work. The motivation here is that if you're measuring a random variable y, and it has some correlation of another random with another random variable x, and you know more about x, like let's say you know the mean of x, you can use what you know about how variable x is to reduce the variance in y, so you don't need as many replications. And this happens all the time in linear regression models. So like this is again a random paper that I've picked out, where they asked this question: how does publishing with top authors in the first 3 years affect success in the 20th year of the academic career? Well, that question is confounded by a lot of other variables like the institutional prestige, productivity, citations. So there's all of these things that likely, if you just want to compare two people in their 20th year of their academic career, how much they've published, and whether they're publishing, and how that's predicted by whether they're publishing with top authors, then you have to also account for these sources of variance. So even though this question only wanted to know what is the effect of top co-authors on this success in year 20, they also had to measure these things: institutional prestige, productivity, and citations. And then they had to calculate confidence intervals for those as well. And so I didn't put those here, but I'm just kind of summarizing that what is going on here is that they, in order for them to get a tight confidence interval on this effect, they needed to also account for these things so that they could subtract off the variance due to these things, so that whatever was left over was the small effect due to this thing. That's effectively, so to speak, what we're doing here. So to make that a little more concrete, let's imagine we're doing this. So let's say there's this power plant, and I want to know, how does a different management strategy affect my daily power output at this power plant? And I could run a simulation of this, or I could be looking at real data from a real power output. And I happen to know that there is a variation in daily temperature that also affects the performance. So I have two management strategies which might affect the performance of the power plant, but also the daily temperature affects the performance of the power plant. So it might just be on cool days, the solar panels run better than on hot days. So I know the temperature. And so the idea is, since I know the temperature and I know whether it's a hot day or a cool day, can I use information about whether it's a hot day or a cool day to get to subtract off the variance due to temperature, so that what's left over is the variance due to management strategy. So that's what I'm going to do here. So the idea here is that my output, which is a performance measure, it's like power output, is correlated with temperature. So I'm going to subtract each output. I'm going to subtract off of it a little bit of basically the difference between that day's temperature and the average temperature, scaled by some proportion. So if I know that today is 10 degrees hotter than average, then I'm going to subtract off some fraction of 10. If I know today is 5 degrees less than average, I'm going to subtract off some fraction of -5. And so before I run my stats on my output performance measure, I subtract off this amount, so that I end up getting a tighter performance measure. And then our question is, what is that fraction that I should be subtracting off? So I'm trying to account for the variance that's due to this temperature. So what does that look like? So this is my output performance of my power plant. This is my temperature of the day. This is my mean temperature. So this is how much hotter or cooler it is over average. And this is some proportionality constant that I need to choose. So I'm going to figure out how to choose that just in a second, but I just want to show you that this new random variable z is an unbiased estimator of y. What I mean by that is, if you take the mean value of z, if you just push it through using probability rules here, the average value of z, the expected value of z, is the expected value of y minus this term plus that term, which just gives me the expected value of y. So that's really cool. So by doing this little trick here, I create a new variable that if I estimate its confidence interval, I will be estimating the same parameter as estimating y. But the trick is I need to try to make the confidence intervals in z smaller than confidence interval y. But if I can do that, if I can make z tighter than y, I need less replicates of z to estimate the same confidence interval. But I'm going to be inferring the same thing. So now I just need to maximize the shrinkage of the variance by choosing an intelligent choice of C here. So how do I do that? Well, I just calculate the variance of my new variable, and it comes out to this formula here, just using probability rules. And then I just take the partial derivative of that thing with respect to C, set that equal to 0, and solve for the optimal value of C, and I get this thing down here. So this is the optimal proportion to put here, which is just the covariance between x and y divided by the variance in x. So if x and y aren't correlated at all, no harm. It's just a 0. It goes away, and I'm just basically z is equal to y. But if x and y are strongly positively correlated, this will be a positive term. If x and y are strongly negatively correlated, this will be a negative term. And so this automatically adjusts z in the right way to compress the variance, to subtract the temperature variance out of y. And then now I can estimate y by estimating z, but I'll have a tighter confidence interval. So that's this is the variance in z. So basically the greater, that's all I'm saying here, the greater these things covary, the greater the shrinkage in variance relative to the variance in y. So a quick example of that is just in sim. Let's say I have a uniformly distributed random number between 0 and 1, and I run it through an exponential. I just take the exponent or the exponential of that number. Pretend like that is a simulation. So it's like I took an input, I ran it through a sim, I got an output. So I would like to estimate the mean of this output, given that I know the mean of the input and I know the value of the input for every one of these replications. So if I do 1,000 replications of this simulation, there's my 1,000 inputs, here's my 1,000 outputs, here is my mean and my confidence interval half width. So it's not too bad. But then if I then estimate this C star by taking the variance of my input and the covariance of my input and output, gives me this proportionality constant. So now I'm just going to subtract off 1.686 times, this value here. So I know all my inputs, I know how different they are from the mean. I subtract off that proportion, and I get then a new mean of 1.72 and a new confidence interval half width of 0.002. So notice that the value, this is the true mean up here. This is a much bigger confidence interval than this one down here. So using the same number of replications, I now have a much, much better estimate of the mean. And then on the flip side of that is if I would have done this to begin with, I could get the same the confidence, of my estimate of the mean with fewer replications, just by controlling for the variance in the input. That's what we mean by control variance. Any questions about that? All right, so these two will be next. And so let's do a quick eye clicker, and that's all I've got for you. So question for today is, how many point estimates should be on your final project report? And that's all I've got. So then we'll see you Thursday. So how many point estimates? So when I scan through when I'm grading your reports, how many times should I see a point estimate? Have a good day.